Hello, today we'll be going over Physics E&M, and this is the Lorentz law. So basically we have a question asking us to find the magnitude and the direction of the net magnetic force from an infinite wire onto a loop of wire. Okay, let's get started. Here we have the basic equations we will need. So the magnetic field of the wire and the magnetic force equation. Okay. Let's draw our diagram. So here we're going to have an infinite wire with I1 pointing straight up. And just to the right of it, we're just going to have a loop of wire with a clockwise current with I2. Now, just for bookkeeping, I will notate some of these corners. So we have A and B, and C and D. And I'll refer to the wire as just the wire. Okay, so how do we get started? So first we need to find the magnetic field that the wire produces. Okay, so this is actually pretty simple. Just take the right-hand rule. Take the right-hand rule, right? So you stick your thumb in the direction of the current. So in this case, it's going straight up. And you can curl your fingers around. Now you see the loop of wires is to the right of the wire. So if you curl your fingers in that direction, the magnetic field will be going into the page. And let's notate our coordinate system. So we have this Cartesian coordinate system. So we have our x hat in the right direction, our y hat in the up direction. And so in this case, z hat will be coming out of the page. So we know that the B field, I'm going to use red, B field will be into the page from the wire. In the negative z hat direction. Okay. So let's document that. So the B field will just be using the basic equation. So mu naught divided by 4 pi multiplied by 2, and this will be I1 divided by R. In this case, let's call this D. We'll call this W, and we'll call this height. So this will just be D, right? And this is equal to our B field. Okay, and this will be in the z hat direction, or negative z hat direction. Now moving on, we basically are halfway done with this problem already. We need to find our force from the magnetic field on the loop of current. Okay, so let's do segment AB first. So let's do the force on segment AB, and this is the force of the magnetic field, and this will just be Q multiplied by V cross B. Okay. And so one transformation I can do from here is I will transform this into the absolute value, the magnitude. So the magnitude of FAB. And the reason I can do this is because I can pretty easily find the direction afterwards with just cross product. And I'll do that in a second. So this will just be equal to Q times the magnitude of V times the magnitude of B times sine of theta. Okay. So we know B is into the page, and we know V, in this case, is going straight up, right? Right here, it's going straight up from B to A. So we know that's 90-degree angles. So sine of 90 degrees is just 1, right? So the F, the magnitude of F on AB is just equal to the charge times the velocity times the B field, all the magnitudes, right? And multiply by 1, obviously. But here I don't really have a charge, I don't really have a velocity that's given, right? There's no nice formula. So I'll do one more transformation. I'll say the force from A to B is equal to the length times the current with the given, which would have given a vector, times the B field, right? Still a vector. Let me stay consistent. Okay. Now some of you might be kind of confused on how this works. I'll explain it at the very end of the video, but for now, just take this as a fact. Okay. So we know the length from A to B is equal to h. This would just be h. I'll notate this in blue. Times the current, which is I2, times the B field, which is just what we wrote above, the B of the wire. And writing this all out, the F on AB is equal to h times I2 times the B field, which is what we had earlier. So it's just this. Here we go. And let's determine our direction now. So earlier we had the cross product of V cross B, which is basically I cross B. And we know I is going straight up. We know B is going into the page. So then the force must be going left, right? You can try that. Point your fingers up in the positive y direction and curl them into the page. You'll see that your thumb points out to the left. So this will be in the negative x hat direction. Okay. So that's our left-hand side. Now for our right-hand side, we see that there's still a magnetic field on the right hand at C and D. So we must take that into account. So let's calculate that. We have F of C and D now. And I'll take the very similar process. We already know that this will just be equal to the length of the segment times the current, I2, times the B field of the wire. Okay. In this case, length is still h, right? From C to D is still h. I2 is I2. And the B field of the wire changes a little bit. So we're going to take our mu naught divided by 4 pi, and we're going to multiply by 2I1 still, but our distance away from the wire is a little different, right? Now we have D plus W. Okay, I hope you can see that. Okay, so let me notate this a little better, and we have D plus W. Okay, now you're asking, well, we don't know what direction this is, and this is still a vector. We had a cross product earlier. We just ignored it for computation. So take a minute and try to think for yourself why this would, what direction would this force be in? Okay, so if you point your fingers down in the direction of I2 from C to D, all right, your fingers are pointing down at the negative y direction. You curl your fingers into the page still. You'll see that your thumb points to the right of the screen, right, in the positive x direction. So this just must be positive x hat. And to find f net, we're basically done, right? F net is just equal to, well, we see FAB is negative x, so I'm just going to do FCD first, right? Because I want to keep everything in the x hat direction. So we're going to do h times I2 times mu naught divided by 4 pi times 2I1 divided by D plus W. I can actually cancel out the 2 and the 4. So I'll just be left with 2 on the bottom here. And I will subtract by h times I2 times mu naught divided by 4 pi, or in this case, we notice we're 2 pi, times I1 divided by D. And this is all in the x hat direction. Okay, So that is our final answer. Now you're gonna ask yourself, well, well, we know it's in the x hat direction, but is it to the left or the right? Right? Is it positive x hat or negative x hat? Well, if we do the by intuition, we know that the B field must be stronger at A to B than C to D, right? Because on the denominator, we see that for A to B, we're only dividing by D, but compared to C and D, we're dividing by D plus W, right? So a bigger denominator means a smaller number, so that means the force on CD must be smaller in magnitude than the force on AB. Right? So therefore, right, 3 dots for therefore, the direction must be negative x hat. So this is your final answer. Okay. Now, some of you might be a little confused, so first let's discuss the transformation of q times the velocity cross b and changing it into the length times the current across b still. Okay. By logic, you might be able to tell that you can kind of reason that, oh, q is charges and it has some kind of speed to it. And on the right, well, I see that we have current, right, which is charges at some sort of speed. But if you want to do the dimensional analysis, it actually works out. So we know q is in units of coulomb, right? And v is in units of meters per second. Here we have units of meters in length. And for I, we have coulombs per second. If we simply multiply these terms together on each side respectively, we have c times meters per second. On the right, we have meters times coulombs per second. We see that these things are equal, right? So our dimensional analysis works out. This is true, right? So transformation works. Now, another thing you might be confused on is, given our infinite wire, right? Okay, you understand that there's a B field going around the wire on the right side, going into the page, and on the left side is coming out of the page. And the current we're observing, or the loop of wire we're observing, is on the right side, so the B field must be going into the page. That makes sense, right? So it's clockwise. But something you might be kind of confused on is, what about the segments AC and BD? So you might be kind of asking, oh, why is this not accounted into our FNet? And the simple answer is they just cancel out. If you want to take the right-hand rule for AC with the B field in mind, right? You point your fingers in the direction of the I2 for AC, which is to the positive x direction. You curl them into the page. You can see that you get a force upwards, right? This is force on AC. Same thing for the bottom side. If you point your fingers in the left direction, the negative x hat direction, and you curl your fingers into the page, right? We're going to see that your thumb points out to the bottom and you get the force of BD. One thing you might want to notice now is, so I is constant, right? So I doesn't change, but the magnetic field does change, right? I'll use size as an example. So at the very beginning, it's going to be much larger. And then the magnetic field gets smaller. And then even smaller, right? Because we're dividing by more and more area, right? It's falling off with 1 over r relationship. But you see that there's a symmetry going on between these two, right? At any given point, we will have the same force, right? Let's say between these two lines, we have the same force. Okay. So they will cancel out. So the FNet in y direction is 0. Right, that's why it contributes nothing to the FNet. Right. Thank you for the time.